Welcome to this lecture series in group theory. In this lecture, we'll be looking at the 15 puzzle and how to solve it, quote unquote, solve it using group theory. Let us recall just one simple fact is that the sign of any transposition is -1. Therefore, if you have a permutation written as the product of an even number of transpositions, then the sign of that permutation would be 1. And the sign of a permutation written as the product of an odd number of transpositions is -1. All right, here are some very simple problems. And now let us look at the 15 puzzle. So imagine this wooden thing where the numbers, each tablet has a number 1 up to 15 written, and this is arranged in a very nice order. So what you can do is you're allowed to slide, uh, a tablet or a button to a blank place if the blank place is available next to it. So you can slide 12 downwards or 15 towards the right. If you do 15 towards the right, then 15 comes here and the blank comes here. If you slide 12, then blank comes here and 12 comes here. And similarly, you can keep, slide this way, then that way, and then that way. So you can slide in a natural way. So the puzzle is the following. Suppose somebody does a little bit of a mischief. What they do is, instead of this 14, they write here 15. I don't even know if this is visible. Let me use a different color. Yeah, maybe this is more visible. So here we write a 15 and here we write a 14. Unfortunately, I need some other color. Maybe, yeah, this one is better. Here we write a 14. And the question is, can you bring it to the original position using non-mischievous moves? So you're not allowed to pull out any button and switch and all that. All you're allowed is just the moves that we discussed. You are allowed to slide things in a proper fashion. So the question is, can you bring this back to the original? Can you get 14 here and 15 there and every other, in the proper arrangement? So it's a very interesting question. The answer is no. And let us see why. And I will be a little bit sketchy, but I'm sure you can make the sketchy proof a formal proof. So let X be the set 1, 2 up to 15 and star symbol. So the star symbol is the blank symbol. So that star denotes the blank here. So every configuration of these buttons can be thought of as an element of sim X, the permutation group of X. So for instance, this mischievous configuration, what is that? This is nothing but the cycle 14, 15. Because all we did was switch the two things. So, right? So at the 14th position, we see a 15. And at the 15th position, we see a 14. So sigma 14 is 15 and sigma 15 is 14. So any such configuration of buttons can be thought of as an element of this guy. Okay. So let me call this sigma, this mischievous position. This is sigma. Okay. And suppose one could solve a given starting position. Suppose one could solve sigma. What does that mean? That means by a sequence of valid moves, you can get it to the identity permutation. So the solved position is one where you have where you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That is the solved position. And the solved position is thus the identity permutation. So if by a sequence of valid moves you can get to the identity permutation, then we want to get a contradiction. All right, but note that if you can at all get to the solved position, to the identity position by a sequence of moves, you will be executing an even number of moves. And that's the crucial observation. Why is that? Why an even number of moves? Because think of this star or the blank. The number of times this blank moves horizontally is going to be even, because it is going to come back here in the solved position. In the starting position it is here, and in the solved position it is also here. So the number of times it moves horizontally should be even, and the number of times it moves vertically should be even, and therefore the total number of times it moves is even plus even, which is an even number. All right, so I should be writing that, but let me not write that step. So the number of moves you'll be making to get from sigma to the identity permutation is even. And every move is a transposition. So every valid move is a transposition. Not that every transposition is a valid move, but every valid move is a transposition, because all we'll be doing is, switching between the blank symbol comes here and that comes there, so it is a transposition. So if at all sigma can be brought to the solved position via a sequence of valid moves, then sigma, you're starting with sigma, and then you have a transposition, then another transposition, blah blah blah, a total of some even number of transpositions will give you the identity permutation. Let me just write as ID, or let me write that as E, right? So some even number of transpositions applied after sigma gives us the identity. But what is this? This is a total of an odd number of transpositions, because sigma itself is a transposition. Therefore, an odd number of transpositions when multiplied gives us the identity. But that's a contradiction, because the sign of this guy is -1 while the sign of this guy is 1. So this particular thing cannot be solved using a sequence of valid moves. You have to break the rules of the game at some point, pull out some button or something, or maybe use a marker to rewrite the numbers, or some sort of that nonsense. Right. So this is a very nice solution to a fairly interesting puzzle. I hope this was clear, and if it isn't clear, then I hope what I have said will help you write down a proper proof. So with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.